Hello to all who are fascinated by ancient architectural mysteries. We present to you the result of many years of research on the Polygonal Masonry of Peru and other regions of the globe, as well as the Nazca lines or objects that catch people's attention with their uniqueness and even mystery. Our approach is scientific, systematization, logic, working with primary sources of information and laboratory research of samples. We will analyze the characteristics of the structures and the technical methods of their construction, trace common patterns and focus on details. Mysticism and speculations have accumulated around this topic. Let us set them aside. By using facts, we will get closer to answering the question about the technologies behind the creation of the outstanding historical heritage of past civilizations. The starting point of our research will be the basic element polygonal masonry. Today, this concept includes various types of walls. We would like to separate our area of interest from all other structures. Later, we will definitely analyze the most famous ones separately. Therefore, the first thing we should do on the path of research is to define terms. Nowadays, the term polygonal is associated with the concept of multi-angle. But what does multi mean? How many is poly? More than 4? But 4-sided blocks are the foundation of many structures. Pisac, Machu Picchu, Huaynapuampa, Agaparka, and almost everything that resembles buildings. So, starting from 4, but that would include ordinary brick masonry or rustication. At the same time, 5-sided blocks are often found, sometimes even 10 or 14-sided ones. At which point does polygonal masonry begin? And if the blocks have only 4 corners, is that something else entirely? Therefore, the number of angles is not the main factor. What matters is that the surfaces where the blocks join are curved, even when the block has a regular shape. As we can see, it's not about the number of sides, and it would be more correct to say this. Dry masonry with minimal gaps made of irregularly shaped blocks with curved sides or polycurved masonry. We can observe that such blocks are not used in modern construction. Standard lot blocks or curved shapes exist, but polycurved blocks have a diverse, unique appearance, ranging from those close to parallelopipeds to more complex forms. Since the term polygonal has not yet gained academic completeness, we will sometimes continue to use it along with polycurved. We will understand polygonal primarily in terms of the shape of the block size, observing curved polygons along the perimeter, and we will associate it with Peru. In addition to curvature, other characteristics of polycurved masonry include: the bottom row of blocks always contains traces of jointing bedding joints in the form of removed rock volume. Because of this, the exposed top part of the masonry row is not flat, it is covered with traces, which sometimes allow for partial reconstruction of the former appearance of the blocks in the upper row. In cases where the masonry is in contact with a rocky foundation, when the blocks are removed, the traces are also clearly visible. Due to the presence of these bedding joints, the blocks were fixed in place, preventing horizontal sliding, making the use of mortar unnecessary. There are no traces of wedge shape cutting or treatment with a chipping hammer point, pickaxe, tooth chisel, or bush hammer, standard stoneworking tools that were widely used around the world. The production of such tools requires durable alloys. However, the tools discovered during archaeological excavations have different shapes and could not have left such marks. The tool marks take the form of furrows of various formats. Distinct sharp edge along the joint line, without chips or damage. Sometimes they appear as sculptural elements, refined and fragile. Any carelessness during processing or installation would inevitably result in defects. In many other regions' masonry, such elements are absent, even though the walls may outwardly appear very similar. Process curved bevels around the perimeter of the block. These are precisely bevels, not chamfers as in ancient rustication and its later versions. The difference from a chamfer is that each bevel has a unique shape and differs in the lower and side parts of the blocks. Their appearance is related to the fact that the surfaces near the joint were treated more carefully. This is clearly visible in the increased frequency of white spots on limestone as the edge of the block is approached. These marks differ in appearance and composition from impact traces left during mechanical processing. On harder stones, the appearance of the bevel resembles a polished surface. The front-facing parts of the blocks, due to processing and the subsequent creation of bevels, have a characteristic convex appearance. Blocks without treated front surfaces are not found. Processing is always present, ranging from rough to high quality. There are no decorative elements in the form of bas-reliefs on the front surfaces. The few exceptions can be attributed to later modifications. They are not systematic and represent primitive, low-quality figures. The high-quality jointing of the blocks is often done with astonishing precision, not just along the narrow edge of the seam, as we often see in ancient masonry, but across the entire surface of the joints. In some cases, narrow jointing can indeed be observed, but this is rather an exception and often the result of imitation or restoration work. The use of hard types of stone, such as granite, diorite, and andesite, is on par with softer limestones and even tuff. The style and quality of the processing and jointing are not significantly influenced by the hardness of the stone. Uniformity of stone within a single complex, only one type of stone is used. Inclusions of blocks made from different stone types are extremely rare and not accidental. Knobs are a consistent attribute of polycurved masonry. They are always located at the lower parts of the block. We should pay attention to the remnants of knobs after processing and their presence on surfaces where processing was not completed. This suggests that knobs, in one form or another, are almost always present. Rare exceptions in the positioning of knobs and the patterns of their appearance will be discussed in a separate video. This also applies to another class of objects, knobs of a specific geometric shape, which are not tied to the block itself, but to structural elements or work sections of rock. To make that happen sooner, you can speed up the release of the videos by supporting the channel with a like and a comment. As we can see, none of the listed characteristics is sufficient by itself to definitively identify an object. Precision of jointing is also characteristic of ancient masonry in Europe. Curved sides are found in specialized blocks. Sharp edges often appear as a byproduct of the manufacturing process. And knobs can be seen on walls all around the world, although their shape and placement differ. The fact that a class of objects is defined by several characteristics may indicate that a key feature has gone unnoticed. This is indeed the case, and we will focus on identifying it. It is obvious that polycurved masonry, like any other, is assembled from blocks. In a single construction, one type of block was predominantly used. However, there are sections where several different types are combined. These variations can be called joint types. Let's move on to their analysis. They vary, and accordingly, the masonry takes on different appearances. Earlier researchers AGURTO CALVO introduced the following designations: rustico, cellular, sedimentario, ingastato, and sycopio, rustic/rough, cellular suggesting similarity to living cells, sequential, and sycopian. As we can see, this classification is based on different criteria: size, similarity to natural formations, and quality of processing. But there should be one systemic criterion. Since we were discussing the number of corners or the shape of the blocks, we will choose that as the primary one. Masonry with 5-6 corners, resembling honeycombs, is hence named the honeycomb type. A characteristic feature of this type is the prevalence of profiles with 5, 6, or more sides. One receiving side corresponds to one natching side, but sometimes there is also a 1-to-2 arrangement. One side is joined with 2. The sizes of the sides are not standardized. The free-form type of masonry. In this case, the perimeters of the front faces do not have strictly defined configurations. The sides can be straight, curved, or rounded. The profile may combine all of these types of sides. A characteristic feature is the use of a receiving profile, which appears as either a sharp or, more commonly, rounded corner. The corner can also be defined by a short, straight segment. Horizontally and vertically, such profiles are typically placed on several adjacent blocks. Four-sided masonry, resembling ordinary bricks or blocks, can therefore be called quadrangular. Its distinguishing features are the prevailing use of quadrangular blocks, with some deviations from the rule, such as when a block contains an angular notch. This occurs when rows of different heights are joined, or when mismatched levels are used with blocks of different sizes. Within a single row, blocks can be similar. The side surfaces often have non-standard slopes. The horizontal sides also often slope, though less noticeably. In some cases, the horizontal and vertical sides are parallel, forming a rectangle. When this type of masonry is used, we see the classic bond between the blocks, where each block overlaps two or sometimes more blocks below. This ensures the basic bond strength requirement. Also, in most cases, there is a decrease in the height of the rows as the structure rises, which, taking into account the sloped sides, leads to blocks of different sizes. Despite their simple form, the blocks exhibit individuality in length, height, and edge shape. An important characteristic of quadrangular masonry is evident in its unfinished sections, where rough, uneven surfaces can be seen. This is evidence that rough stone with ample volume was used as a base block. The final shape was given during the construction of the wall. All the types of masonry mentioned predominantly consist of relatively large blocks, or they contain individual megaliths and rock formations. The shape of the blocks and the way they are joined together determine the characteristic appearance of the structure, allowing the complex to be recognized even by small sections. This raises the question, how is it that each complex possesses its own individual features and style? In the framework of a single architectural school, reliable solutions are developed and then spread everywhere. The size of the structure and the number of standard elements, such as columns or openings, may change, but the structural principles remain consistent. These principles are passed from one building to another with minimal alterations because they have proven their reliability. Other methods must undergo a long evolution, including trial and error, with issues being resolved along the way. However, we see different styles already in their fully developed form, as if the builders possessed unlimited knowledge and applied it whenever possible. We can observe a wide variety of masonry styles, both in terms of the way blocks are joined and their sizes. The foundations also vary, ranging from extremely stable bedrock and megaliths to more unstable masonry made of small stones. What level of confidence must one have to use such foundations? It is impressive that each chosen solution proved to be suitable. The amount of natural destruction is minimal, and most of the loss of integrity occurred when structures were dismantled for use as quarries. Natural disasters had little impact on any type of masonry. The formation of polycurved masonry is determined by the following principles. The first, basic and elementary principle, masonry is created not from a single block, but from multiple blocks, representing their joints. The second, the perimeter of each block is a combination of receiving and responding sides, which form the joint profile. The third, in polycurved masonry, the quality of the joint is ensured by the fact that the sides of the connected blocks conform to each other's configurations. These three fundamental components form the basic rule for polycurved masonry. It can be referred to as the rule of receiving and responding profiles. Many aspects of block placement are strictly governed by this rule. It also has numerous practical applications, one of which helps clarify the sequence of block installation. Thus, the side surfaces of polygonal blocks can be divided functionally into receiving and responding profiles. The receiving profile is essentially a prepared seating surface for the next block in the masonry. The responding profile is the side of the next block, the shape of which must correspond to the seating surface. The seating surface can be located entirely on one block, but more often it is formed by two, or sometimes even three neighboring, already joined blocks. At the same time, the seating surface is not a chaotic set of surfaces of closely placed blocks, but always a unified surface brought to a single common level. The profile of the seating surface, or, simply put, the receiving profile when viewed from the front, has a distinct silhouette. By highlighting such a silhouette, we can describe the configuration of this entire receiving profile and form an idea of it without dismantling the masonry. This is due to the fact that the main features of the profile are preserved throughout the depth of the joint. The configurations of receiving profiles vary widely, from perfectly straight to S-shaped curves. Among them, several well-defined types frequently recur, each with certain variations. Straight receiving profiles. These profiles either take the form of a perfectly straight line or a slightly curved one. Horizontal, vertical, and even straight diagonal joint lines are formed by this type. Curved profiles. Receiving profiles with more pronounced curvature form another type with its own set of distinct characteristics. We can tentatively call this type the arc. Straight and curved profiles appear in those rare cases when the joining of blocks occurs along only one side. Either horizontal for the first block of the masonry or lateral when there is no need to fit the block to a foundation. Typically, the installation of the next block required the fitting of two or more sides, horizontal, lateral, and sometimes even the rear. L-shaped profiles. Next, we have a profile resembling the Latin letter L. The bent angle of this profile can be right, obtuse, or acute, and may have varying degrees of rounding, either smooth or, on the contrary, sharply accentuated. The angle may also be truncated by a straight line. U-shaped profiles. The configuration of this receiving profile resembles the Latin letter U, but with one shortened vertical side. In some cases, the shortened side is so small that the profile resembles more of a modified L. This seating surface typically fills a deep recess and touches the side of the block adjoining it from above. All of these profile types share a common feature: receiving blocks were adapted to fit the shape of the responding block. It would also be logical to expect the opposite, situations where, due to structural requirements, the shape of the installed block had to be modified. Such a characteristic is found in the double L profile, where the joint includes an additional angle, resembling two sequentially placed L shapes. Sometimes this profile has smoother contours or a relatively small vertical section. It is most common in quadrangular masonry, while in free-form masonry there is only a single concentrated area featuring it in a small section of Ollantaytambo. In other cases, it is rare in this type of masonry. Another variant occurs when the receiving area is not level to a single plane but formed with two sloped top edges of the blocks. In this case, the corresponding block takes on a keystone shape with a downward projection, while the resulting profile looks like two curved L shapes directly extending from the double L profile. Occasionally, several projections form, but this does not change the profile type. It's also worth noting that the keystone projection may match only one corner of the receiving blocks, or it may be of minimal size. At this point, it becomes clear that all the examined jointing methods can be described as transformations of the L profile. The increased complexity in jointing leads to a different fitting process, where after test fitting, it is the block itself that needs adjustment rather than the receiving area, which would have been more convenient. This must have required additional effort. In many cases, surfaces could have been leveled to avoid these extra labor requirements. The fact that this wasn't always indicates the versatility of tools or fitting methods available. In certain instances, the downward projection was actively used in quadrangular masonry, causing the shape of the blocks to resemble free-form masonry. Therefore, a strict division between masonry types is impossible, as a limited set of profiles naturally leads to forms based on the same foundational principle. In addition to the receiving profiles discussed, there are examples of very complex joint shapes. However, these do not correspond to profiles associated with the joint line, but rather to the directly contacting surfaces, whose structure changes with depth. As a result, the edge shape of the block sides forming the joint line does not always perfectly match the curvilinear configuration of the side itself. Identifying receiving profiles as separate entities helps to resolve several questions. The first, most basic, and fundamental property that identifies polycurve masonry. During the profile making process, a significant amount of stone material was removed comparable to the size of the finished block. This applied regardless of the type of masonry. This work was carried out simultaneously with fitting the blocks together. Before the block was installed, the rough stone was surface worked to resemble a rounded river cobble. Thus, the defining characteristic of polycurved masonry is that it is constructed from roughly shaped stones of arbitrary form, based on jointing profiles, accompanied by the formation of bevels, knobs, sharp edges, and precise jointing. The quarries were natural rockfalls located at the construction sites Pisak, Ollantaytambo Terraces, and the Temple of Ten Niches, Sacsayhuaman, Kilarumiok, Chinchero, Machu Picchu, Urukrumi, and others where local stone was always used. This means that quarries, in the traditional sense, did not exist. In a quarry, blocks are purposefully shaped. When manual labor is used, especially with soft stone, trenches must be dug for each block, leading to significant volumes of stone removal. By working with natural rockfalls, labor is reduced, as suitable stones can be selected based on their shape. It is crucial to note that the stone was treated at the quarry, not at the construction site, which reduced transportation effort, as the portions of the stone that would be discarded were not moved. It also made it possible to produce nearly finished blocks, which required minimal adjustment when joined together. However, this work sequence was not followed for polygonal masonry, where the block shape was unknown in advance. Even in the case of quadrangular masonry, all the block performs varied in size. In the example of a block from a dismantled wall in Pisek, we can observe that the sides not involved in jointing retain the appearance of rough stone. This suggests that, prior to installation, the block performed had a form close to its natural state. The only core is associated with polygonal construction or kachikata, which supplied material for the Ollantaytambo Sun Temple, as well as Rumikalko and Hyokoto, presumed sources for Coricancha and sites around Kaskar. However, these sites stand out for specific reasons. The first has its own unique history and construction context. While andesite transportation was essential for structures in Cusco since this rock is absent within the city limits. In other cases, there are no known quarries even though dozens of polygonal complexes exist. At the Rumikalka quarry, blocks processed on all sides remain to this day. Similarly finished stones can be found in Hyokoto. In contrast, in polygonal masonry, the upper and rear sides of blocks are typically rough and unfinished. The facade sides often had extra material before fitting, some of which would remain as protrusions after jointing. Yet in the quarry, finished blocks with smooth facade surfaces are found, without any knobs since they were unnecessary. Producing such features would have been meaningless unless for imitation purposes. Additionally, there are significant piles of stoneworking debris in the form of fragments. Such waste is characteristic of stone shaping with a chisel. When stone is worked using stone tools alone, the residue is primarily fine dust rather than fragments. The blocks also lack typical traces such as grooves and rectangular depressions, which are characteristic of polycurve masonry. This combination of discrepancies processing on all sides. Finished facade surfaces without knobs, abundant fragments of waste, and the absence of characteristic traces strongly indicates that these blocks are most likely the result of later uses during the Spanish period. During this time, blocks were worked not only with stone hammers but also with sealed tools. The second practical implication of defining jointing profiles, as mentioned earlier, is determining the order in which the blocks were laid. For example, at Saxe-Uemen, the blocks could only have been laid in a numbered sequence and only consecutively as the corresponding receiving profiles were created. Third, since the rule of receptive response profiles dictates the sequence of masonry assembly, it is possible to identify not only the order in which the blocks were placed, but also the starting point of the structure. This is an important aspect for understanding the logistics of wall building. It may help to answer the question of why, within a single complex, walls are built in different styles and even with different types of masonry. One can also examine the methods used to connect separate sections. A detailed analysis of such technical aspects allows us to clearly see what was happening on the construction site during the initial stages of building in the distant past. Fourth, if the top row of masonry is removed, what remains is a set of receptive sides with a characteristic appearance of individual sections of joint profiles. This is especially striking in the free-form masonry. Now, let us compare this result with the top rows of certain structures. It is clearly visible that in the upper part of the blocks there are no traces of fitting them to the next row. There are no remnants of joint profiles, meaning this is not a dismantled or damaged masonry, but rather an unfinished section. Construction work was halted for unknown reasons. Perhaps the builders decided that the current height was sufficient, even though nearby the masonry is taller. When the necessary material ran out, we will discuss in future videos that not just any stones were used. Technical reasons may have intervened as well as natural circumstances. At this point, what is important is that we can observe distinct stages of the work in this sequence, bringing us closer to answering the key question how exactly polycurve masonry was constructed. Fifth, the creators clearly followed the natural laws of stress distribution. These principles are visible in nature, for example, in the structure of cellular tissues or the arrangement of veins on a dragonfly's wing. In masonry, this manifests through the minimization of joint lengths. This can be demonstrated by calculating the length of joints in the case of straight and rounded corners. Defining the length of the segment under consideration as A, for straight angles the total joint length is 6 times A. For an angled corner, it is A times the square root of 2 times 4. For a curved joint, it is 6 times A. This results in either equality or an advantage. Sixth, joint profiles are one of the basic characteristics of polycurved masonry. This allows us to determine its authenticity. Let us examine modern imitations and compare them based on all the mentioned criteria. We see that the blocks are made of different types of stone, and the precision of the joints is absent. The bevels are created for decorative purposes by rough splitting, and there are no knobs. The front surfaces of the blocks are rough, while they should be smooth. The depth of the joints is small, and instead of being curvilinear, the joints are flat. There are no traces of fitting work in the form of receptive surfaces on the blocks. The imitation itself is done in the free-from style. If we analyze the execution of profiles, it becomes clear that they are also misaligned. In the original masonry, an L-shaped profile encompasses several side surfaces of the blocks, flowing smoothly without bends. In the imitation, breaks are present. A jagged line of joints is characteristic of honeycomb-type masonry. As a result, the profiles correspond to one type, while the block shapes belong to another. Due to the incorrect execution of profiles, a block was created with a shape that is not found in polycove masonry. As a result, the inconsistency arises not only at the level of joint surfaces, but also in the adherence to the overall construction rules of the masonry. Therefore, despite significant external similarity, the masonry differs in nearly all key aspects. The multiple differences from polycove masonry are caused by different methods of block fabrication and basic construction principles, where there are no knobs, bevels, or traces of fitting. The principle of joint profiles is not followed. Thus, through a systematic approach and the correct terminology, we have developed a working method for distinguishing masonry types based on specific characteristics. The seventh addresses the speculation that the material of the blocks were assembled clay during construction or that geopolymers were used, resulting in phenomenally tight joints between the blocks. However, the rule of receptive response profiles demonstrates that the fitting of polygonal blocks is the result of proper preparation of the block's side surfaces, which were in a solid state. Otherwise, how can we explain the fact that significant volumes of rock had to be removed, both in the masonry and in the case of fitting the blocks to the rock face? For example, limestone blocks, which are relatively soft, had their receptive profile shaped in hard diorite. Liquid material would have simply been poured, sometimes without even treating the surfaces. But we see the opposite situation. All the joint profiles are perfectly smooth, without bends or roughness. There is not a single example where a block filled a rough gap. Cast imitations, on the other hand, result in wavy joint lines. Moreover, all blocks constrained by space have a wedge-like shape, which enabled their placement in a solid state. There are no examples of negative slope sides, nor are there any cases of cavities or gaps between the blocks being filled. Each block has a shape corresponding to the required profile, and in the same place, we can see how the builders decided whether to give a block a locking projection or not. The complete list of arguments against the geopolymer hypothesis is extensive, but even these discrepancies are enough to disprove the idea that plasticity of materials capable of filling a mold were used. Moreover, the geopolymer hypothesis complicates the issue, raising more questions than answers. Eighth and final. The remnants of profiles in the form of small indentations on blocks allow us to determine whether a block had previously been in the masonry. This makes it possible to distinguish between unfinished block stones with pre-processed surfaces that were only prepared for installation and blocks from dismantled structures. Thus, we can trace the transformation of rough stone into a polygonal block. This also includes the ability to reconstruct structures from scattered blocks. Thanks to the individuality of the blocks, determined by the creation of profiles, and especially by using modern digital tools, it is possible to restore the masonry in its authentic form. Unfortunately, many blocks remain unused, lying scattered near the complex. However, we can observe small examples of such restoration at Ollantaytambo. In older photographs, a block was missing, but later it was put back in place. The same restoration process was applied to Saxe-Heumann, using authentic blocks found nearby. When examining the profiles, it gives the impression that there was no single template for them, and each one was created according to the specific situation. There seemed to be no constraints apart from those dictated by the shapes of the stone blanks or the configuration of the masonry itself. This could indeed be the case, as each blank was unique and the entire construction logistics would need to account for this condition. However, defining joint profiles as a separate class of objects reveals that certain structures often emerge. In some instances, these structures exhibit full or partial symmetry. In others, staple patterns of a general type take form. Given the aforementioned variety in the shapes of the stone blanks, these formations can be considered intentional and worthy of dedicated study. It is also worth noting separately that the presence of blocks with complex side configurations contradicts the impact technology. To produce blocks through mechanical processing using stones, for example, the most rational approach would be to create blocks in a shape close to a parallelepiped, with minimal adjustments once the blocks were set. If a block were damaged, corrections in the form of insertions would be needed, and indeed they are sometimes found. However, in the general case, the opposite is observed. It seems that the creators were not concerned with the need to remove significant volumes of stone directly within the masonry. The same principle is observed in the carving of recesses in the rock for block placement. However, these recesses are often mistaken for the locations of previously placed blocks, with these remnants of masonry being interpreted as standalone features. When conducting experiments using impact methods with stone hammers to demonstrate the possibility of achieving precise block fitting. First, precise fitting is not replicated and a significant gap remains. Secondly, the fitting is done between two surfaces, not the entire joint profile, which involves at least two sides of already placed blocks. Moreover, the fitting should be performed not on individual stones but directly in the masonry. When processing passes through already joined blocks, brittle edges will be damaged by the impacts. The majority of polygonal complexes are constructed using freeform masonry. Quadrangular masonry is used only for structures resembling buildings. Therefore, the reproduction must also focus on free-form masonry, with block sizes close to megalithic proportions. As a result, such experiments often serve the opposite purpose. They demonstrate that this method of processing produces a completely different result, a block-type masonry with mediocre joint fitting, using smaller stones, without forming authentic edges and knobs. Some aspects of joint fitting simply cannot be explained by basic impact processing. For example, how is a flawless recess made for a tiny protrusion on one of the block S-edges? Such an element would be unnecessary. In simple manual processing, it would be easier to remove it and then continue fitting. Therefore, the work followed a principle where even the smallest details on one side were matched to the opposite side, resulting in a perfect fit. This points to the need for discussing not just the mechanism of stone processing, but primarily how the control of jointing was ensured. An additional consideration, we have determined that due to the execution of joint profiles, the individual creation of masonry blocks is only partially possible, as the exact position and shape of the next block are determined by the placement of the previous ones. In fact, this can only be described as creating block performs roughly shaped stones with surface level treatment. If the corresponding part of a block were made outside of the masonry, there would be visible mismatches, as seen in imitations where the pre-treated surfaces have varying areas. The inability to create blocks in advance makes the use of a large number of workers impractical. There simply wouldn't be enough work for them. At any given moment, only one block needs to be fitted. The only solution is to start construction from multiple points, and indeed, this approach was used. However, this method does not significantly speed up the process. Even if, instead of one section, 4 are being built simultaneously, it would still require only 4 masters, while thousands of laborers would remain idle. In contrast, when imitating, it is possible to create molds and fabricate all the blocks separately, then assemble the masonry. However, due to inaccuracies in both the creation of the blocks and the assembly, gaps are present, which is what we observe. In addition to the masonry with distinct polygonal features, there are sections in the complexes where the blocks are not joined as precisely. These sections lack the characteristic elements that are consistently found in the previously discussed type of polygonal masonry. There are no knobs or pronounced bevels. The sharp edges of the blocks are not emphasized and are barely noticeable. The quality of the jointing between the side surfaces also differs. Many are not fully jointed, though there are some joints of very high quality. At the same time, the front surfaces of the blocks may be processed quite meticulously. This type of masonry cannot be classified as polycurve masonry, yet it leaves no doubt that the same builders who constructed the upper walls were responsible for it. The quality noticeably improves as the construction rises, while still retaining the overall style. Some blocks are joined flawlessly, and the same can be said for the corners of the walls, which bear a heavier load and are therefore carefully constructed. As we can see, even partial fitting, combined with large blocks and adherence to the profile principle, prevents block displacement. This, along with the inclination of the wall and its stabilization by the embankment, ensures the masonry's strength. The damage to the lower tier is not so much due to low quality jointing, but rather the greater height of the wall compared to the upper tiers and the effects of water undermining during heavy rains. What could explain such a difference in execution? The idea of different authorship has already been considered, and it is not in question. The answer, then, lies in either a desire to reduce labor costs or the absence of a need for precise fitting. As will be shown in further research, a combination of both factors is present. Additionally, it should be noted that the terraces of Ollantaytambo are not the only example of this. Differences in execution can be found in Machu Picchu and other complexes. In Saxe-Huaman, for instance, the difference in the execution of the levels of the zigzag walls is also noticeable. A particular type of masonry, executed with megaliths of partially corrected shapes, deserves special mention. In these cases, small stones are used to fill in the gaps and avoid long joints. It is clear that the megaliths have been worked with smooth front and side surfaces, while the broken stones have a more angular appearance, as seen in the rock fragments nearby. In conclusion, we can affirm that the creators of the Polygonal Masonry did not shy away from simplified solutions when possible. But how, then, can we distinguish between various megalithic masonry and natural formations in the scope of research? First, we can clearly define that this is not polygonal masonry, as it does not follow several key characteristics: the precision of joints, the presence of connection profiles, and the associated curved bevels. Next comes a key feature. Masonry with partial joints is never the central place of a complex, it is always found on the periphery. Thus, it serves a secondary or often utilitarian role, such as retaining walls to prevent landslides or separating the complex from its natural surroundings. Such structures are not functional on their own. Therefore, if a structure with partial joints is a central element and there are no other components of the complex nearby, such as rocks, woodcuts, or polycurve masonry buildings, then we are likely looking at architecture from a different culture. Or perhaps it is a natural phenomenon altogether. And of course, it is important to touch on the topic of high-quality imitations, both in modern times and in the past. In modern restoration work, traces of a bush hammer can be seen in groups of marks corresponding to the shape of the tool. These traces may be left intentionally as a marker to distinguish ancient masonry from modern repairs. Similar markers include carved dates or special notches. Pyatkin and CUSICANCHA have both been extensively restored, and this can be observed through photo comparisons and detailed reports on the restoration processes. Thus, the level of quality achievable with modern tools can be observed firsthand. However, as one individual involved in the reconstruction project stated, there are joints so tight that not even the tip of a needle can fit. We cannot achieve the same results. We can only make something similar, like what was done on Laredo Street. The stones are tightly fitted only on the surface but never throughout the depth, as the Incas did. The point is that in modern restoration work, the tightness of the joints is only achieved near the visible seam, while in the authentic masonry, the stones were fitted perfectly throughout the entire depth. Moreover, priority is given to using original blocks found nearby during restoration. Therefore, the facade of these blocks will retain all the characteristics of authentic masonry. Combined with well-reproduced joints, such restorations can look comparable to the original structures. Fitting using a stone hammer is demonstrated in the work of J. Protzen, where the gap between the blocks is clearly visible. This illustrates the quality that can be achieved by working with simple tools from past eras. Thus, adhering to a scientific approach, based on data and maintaining impartiality, it can be reasonably argued that the INCAS were capable of producing relatively high-quality quadrangular masonry. With some deviations, such as the smaller size of the stones, not as perfect joints, and possibly the absence of angled sides, yet still very close to polygonal masonry. The honeycomb type, due to the linearity of its profiles, is also reproducible. This is evident in modern restorations and could well have been actively used in ancient times. There are many examples of well-fitted small blocks, but the differences from the original masonry are obvious. Additionally, the honeycomb type is extremely episodic, and Taohuasi is the only complex where it was extensively applied. In later works, the honeycomb type is used widely due to its ease of execution to just give the edge a natural stone shape. As for the reproduction of free-from masonry, the only example in Cusco remains unfinished. This is evident by the fact that the sides of the blocks were not shaped to fit the corresponding joining profiles. This means the construction was interrupted. How can we explain this peculiarity, where, in the center of the capital of stone architecture, an unfinished object remains, while on the outskirts, complexes made of thousands of blocks have been erected? The only possible answers are a lack of skills or resources, perhaps the necessary stone ran out. Resources can be dismissed since imitations often disregard the rule of using a single type of stone, as can be seen right here on another corner, where the masonry was continued with blocks of a different type and size. Therefore, the obstacle was the absence of skills or tools. In future editions, we will cover the technical execution of polygonal complexes and rock-cut cavities. Hit the bell icon so you don't miss it. Thank you for watching and for supporting the research, which you can show with a like, subscription, your observations in the comments, or a donation.